So this is going to be the second part of the lectures on superconducting qubits, and I use.
You should switch it on, no? It is. Yeah, it is.
The laser is, but it doesn't. Somehow it doesn't want to talk to me. It doesn't matter. I will just hint. So, Lisa, I have a second chance to thank the organizers for inviting me, especially Herman, for giving me the chance to be here and then give you some more flavor about the world of superconducting qubits. In fact, most of what Leandro said is what I was planning to say today, so that's good because I will be able to focus on the rest of the parts, because I assume now you're experts on circuit QED. Yesterday we were left with the last part, which was about the coherence, and I think it was a good choice to leave it for today, because when you talk about the coherence, you talk about the physics surrounding the qubits, and that is one of the, let's say, capabilities of these qubits, that they're able to sense the microscopic environment around them. I also wanted to add one slide, and this was motivated by a question from Leandro from yesterday. How do we drive these qubits in situ? So this is one of these charged qubits, one of these transmon qubits. Topologically, it is the same as these other ones that had these interdigitated fingers. What you see, this cross is actually the one of the capacitor plates, and then the ground is the other capacitor plate. So this is just the capacitance of the qubit, and right here you see the loop with two junctions, so that's the squid. And down here you see two lines coming in. This one is an antenna, so it's a coaxial, is a coplanar waveguide that ends in an open circuit, so it's disconnected, which means that the electric field will be strong at that point. And this line is used to drive microwave pulses, to drive qubit transitions. Next to it, there is this line that is also like a coplanar waveguide line that is shorted, similar to the resonators that Leandro was talking about. Because there is a short, that means the current will be maximum at that point. And so near where we have our junction loop, our squid loop, we will get like strong currents. So this line is used to modify the qubit splitting fast. On top of that, there is a DC current flowing here to like fix the background current. This is for these transmon qubits. For the flux qubits, I took this work from the MIT group, where in this case they had two of these qubits. This is one of them, the three junctions. This is the other one, three junctions. And then they have, again, these coplanar antennas that they are shorted at this point, and these are used to drive flux into the qubits. This can be used to drive slow flux or fast flux, depending if you are just modulating the qubit frequency or you're inducing transitions. Okay, so let's go to talk about the coherence. So yesterday I talked about, and Leandro also explained, how to control the qubit state. But because these qubits are not living in vacuum, there are many processes that take energy away from qubits and also modify their energy splitting. I list the major obstacles here. There's some more, but in the interest of time, I only wanted to highlight these. The first one is the noise you get from your control lines. So a quantum system, like the ideal quantum system, is one which is completely isolated from the universe. But then you cannot access it, you cannot read it out. So you always have to poke it. And that means opening this system towards the rest of the world. And that means you have to make it a bit lossy. You have to extract information from it. And depending on how you design the circuit around the qubit, you may actually kill it completely. Because all our measurement lines, they are connected to the outside world, to some impedance, and this impedance is a normal state resistor that produces Johnson noise, and this is a source for relaxation and dephasing for qubits. So with a good design, a good set of filters in your lines, this one can be cancelled out. And even though it sounds like the trivial one, in fact this one took a long time to nail down, to understand how you had to design a proper circuit to get long coherence qubits. Once this one was away, then the next one came in. So infrared radiation. So in dilution refrigerators, the temperature of the fridge, the lowest temperature is a few millikelvin. But the chamber, the inner chamber or the outer chamber, it doesn't matter, has photons coming from the shields of the fridge, which are radiating, black body radiation. If you take the Planck spectrum of a body at 3 Kelvin, you see it peaks at about 170 gigahertz. And the aluminum gap is near 100 gigahertz. So we're very close to the Planck peak. That means there's a lot of, or there's a certain amount of power that is generated so there's photon generated near the aluminum gap. That means they can induce loss. I mean, there's also higher energy photons can also break Cooper pairs. So this is a problem. And once people understood that this could be a real problem, then the idea was to remove these infrared photons. And for that, people went to the work by NASA, which is in their satellites, they coat them with some absorptive material to prevent them from heating up. And this material is made of mostly silicon carbide in a kind of like a glue. Sticas is a good assembly glue, and coating the bottom of the mixing chamber of the fridge. So with this material, which has about 90% of absorption in the infrared, then they were able to demonstrate, so different groups in parallel, they were able to demonstrate a significant improvement. The Santa Barbara group, they did it with just a resonator. So in red, this is what they measured before this coating. So at low temperatures, they had a quality factor of about 10 to the 5. After adding this coating, the same device, cooling down again, then you see this increases by an order of magnitude. So there's already a significant amount of loss that the resonator was experiencing before. The IBM group, they also did it with a superconducting qubit, where they actually coated the whole qubit, the box where the qubit is sitting, with EcoSorb. EcoSorb is a material that is mostly absorbing microwave radiation. And the problem is that in that experiment, once they had completely coated that box, it was not possible to open it again. So that device and the box were done for good, but at least they were able to demonstrate that before and after, there was about a factor of 10 improvement in the lifetime of that qubit. So there is a lot of stuff going on, not only in your leads, but also in your what you think is vacuum. So this is done, so we can forget about it. Next one. This one is the real deal to beat. This is the two-level system. This is the 1/f noise. In fact, this noise was also mentioned yesterday at the talk of Dieter. The flux noise that is being detected, sensed by squids, which has an amplitude which goes by about a microphinot per square root hertz, and then it's a 1/f spectrum. So the same kind of noise is observed by qubits, all kinds of qubits. This is a plot of the power spectral density of noise by using one qubit, a single flux qubit. And the different points correspond to, this is a frequency space. This starts at a few kilohertz and goes up to gigahertz. So by doing dynamical decoupling techniques, they were able to extract the amplitude of the noise. And you see that it follows this slope, which is 1/f to the power of 0.9. So it's not exactly 1/f, but it's somewhere close. Also, there is quite some dispersion. There's other data that I don't show, but people were doing different measurements. They were able to map out the other end of the spectrum going well below a millihertz, and they still find this 1/f. And even this is from 2011, so this is not the most updated, but people have been able to extend this trace, and it seems like the 1/f goes all the way up to the gigahertz. So the same element that is causing this noise is actually producing decoherence or dephasing and also relaxation in qubits. So it's a very broadband spectrum. So the question is, what is causing the noise, and how can we deal with it? So this question has been in the minds of people for a long time. I mean, the squid community from the 80s were already puzzled by this. And when the qubits appeared, the same problem comes back again. So the qubits are sitting on a substrate, and this substrate may have charge traps, so some irregularity, inhomogeneity in the substrate that has that some element. It could be an electron, it could be some dangling bond that has two stable positions, but it can switch between them. So this can cause charge noise, but if it has a magnetic dipole, it can also cause flux noise. Could be trap vortices, nuclear spins, so you name it. This is a measurement of a qubit from the Santa Barbara group, so long coherence qubit, as a function of time. So the horizontal scale is, this is not function time, this is just frequency. They just take T1 measurements because they can tune the frequency of this qubit. It's a relaxation time measurement for different frequencies. And you see this structure that is very like jagged. And if you zoom in, you see like peaks in the relaxation rate of the qubit. So this indicates, this is consistent, this is simulations that they performed. This is consistent of multiple two-level systems that are resonant with the qubit, but they interact weakly. But because there is many of them, this causes the qubit to relax. Even though they're not strongly coupled, the combination of all of them causes this fluctuation in the decoherence. So they're also responsible for relaxation. But very recently, actually this year, there's a group in the UK, in the NPL, that they started to shine light in the origin of the problem. What they did is actually a very smart experiment. They just performed ESR on the substrate. So something that we could all have thought about it before, but essentially what they did, they just made a niobium nitride or a niobium resonator, and then they applied magnetic field and looked at the quality factor or the frequency of this resonator. And in this way, they were able to single out the different elements that had the magnetic response. You can see the trace here in the red one, that they had peaks that they could identify with hydrogen, two types of hydrogen, and then this is from electrons. So there is a clear evidence from this work that this noise is coming from radicals of hydrogen or OH that are sitting on a substrate. And this can come from water, comes from oxygen in the air, recombines with the water. So basically, what you need to do is get rid of those. And what they did in this experiment, they took the same device, they put it in a vacuum chamber, and they annealed it. I think it was at 300 degrees for a few hours. And then they took it back to the dilution fridge, cooled down again. And then there's the blue trace. So they don't show the data here, but basically there is nothing. These hydrogen peaks are gone. So by annealing the substrate, they were able to remove these leftovers from your chemistry. Here is, actually this is this picture here. So you see the blue is just flat. So this is the ESR spectrum they were observing from these resonators. But then if you look at the noise, the power spectral density of noise for these resonators, you see the red ones was before this annealing and the blue is after. So you see a decrease of, on average, almost an order of magnitude of this noise. So this is actually very good news, because decay rates scale with the square of this quantity. So reduction of a factor of 10 in noise power spectral density is 2 orders of magnitude of enhanced relaxation or decoherence in general. So this is just very recent. So now people have to start applying these to qubit devices and see if there is a similar kind of response. So let's say it's work in progress, but I'm almost tempted to cross it out completely. Next, we move to quasi particles. Leandro has talked a lot about quasi particles, so that's good because you already know what this is about. I wanted to mention an experiment from the MIT group where they actually were the first, to my knowledge, this was the first time that an improvement was made so that they were able to get rid of quasi-particles for a short time. And the idea is the following. This is their device. This is one of these flux qubits. You can see the qubit loop here. This one had 4 junctions. And then there is this outer loop, and that's a DC squid. So they actually used the DC squid to detect the flux from the flux qubit. This is the old style, how people measured qubits before the resonators came in. But in this case, because this qubit is connected to some leads, so that seems to, let's say, that seems to lead to a lot of quasi-particles coming in. So because there are several islands, one of these quasi-particles could be jumping back and forth between these islands, but if it jumps to the ground, then it goes away. And what this group thought is that if we excite the qubit and we let it relax because of a quasi-particle, then maybe this quasi-particle in the relaxation process will pick up the energy from the qubit and will escape. And then they demonstrated that this is a decay time of the qubit, by applying a pi pulse, a sequence of pi pulses, they were able to enhance the lifetime of the qubit because they were removing these quasi-particles. So, and as they managed to increase the T1 time, I think it was about a factor of 2. But the quasi-particles kept coming in. So this was something that is very strange, because if you look at thermal equilibrium, you take the Boltzmann distribution at the millikelvin temperatures, there should be nothing. So this is a non-equilibrium population of quasi-particles, which keeps people puzzled. Another important experiment related to quasi-particles was performed in 2014 by the Yale group, the Michel Deborah's group, with another type of qubit that I didn't explain. And I wanted to talk about this experiment because it has to do with a very fundamental debate from Josephson physics. This has to do with the quasi-particle tunneling. I think it was mentioned in Dieter's talk yesterday. So in a Josephson junction you have Cooper pair tunneling, but you can also have single charge tunneling. And this single charge tunneling goes with this term that has the cosine of the phase, and then there is this prefactor epsilon. And there was a long-standing debate about whether this epsilon is +1 or is -1. People couldn't agree. There was no definite measurement who could reliably determine this coefficient. So in the Yale group, they had designed this qubit, which is essentially a small junction shunted by a gigantic inductance. This inductance is actually a chain of big junctions. They call it superinductor now. And the thing is that this qubit is supposedly protected from charge noise, and it's also quite insensitive to flux noise. So they were able to bias this loop at half a flux quantum, and this is the relaxation time of this qubit. You see it's in the 100 microseconds already at the worst point, and then near half a flux quantum it picks up and it reaches a few milliseconds, which is remarkable for qubit. This is among the best. This is kind of like the state of the art in relaxation times for qubits. And their argument was that here what's going on is that there is a suppression of quasi-particle tunneling through the junction, and that means this coefficient epsilon should be 1. So they managed to solve a debate from Josephson physics from lasting decades, and it's related to quasi-particle tunneling. But the problem is not solved. I mean, there is a lot of physics behind. People are trying to build traps, vortices to trap these quasi-particles, but there's no solution. I point here cosmic rays because there's already been more than one person that has suggested that the cosmic rays, I mean, we are constantly there's cosmic rays everywhere that are going through us at the moment, anytime. So they also go through our devices. And superconductors are very good photon detectors from all kinds of energies. So perhaps this quasi-particle generation has to do with cosmic rays. So this may sound a bit insane, but perhaps there is some truth behind. So this may be some line of exploration in the near future when people start getting desperate. But nevertheless, this is the important plot. Nevertheless, despite that there's still some loss mechanisms existing in these circuits, the trend is like very steep increase of coherence time. This is a summary plot from that Will Oliver from the MIT group compiled. Starting in year 2000, where lifetimes were in the nanosecond scale, numbers have gone up to a few microseconds, and now even into the milliseconds. Here the result I just showed is missing. It should be up here, this fluxonium. I think this is basically not up to date. And this line here is very important because when you exceed this point, that means that your qubits are good enough that now you can start to think about designing error-correcting protocols in your device. That means you have a qubit that you want to control its state. You don't want this state to decay. And in order to do that, you build another circuit around it, which makes sure that this state will never decay. This other circuit consists of many other qubits. So it could be that these correcting qubits also have some errors. But if you put enough of them, this error suppression will be decreased. And the best theory, or let's say the best scheme that theorists have come up with, is called the surface code. It's a planar structure, and its nearest neighbor. The problem is that the overhead number of qubits is on the order of 100. That means you need 100 qubits to stabilize a single qubit. That is if you are at this point. But if you can exceed that number, this reduces the number of overhead qubits. So as qubits get better and better, then you will not need so many other qubits to correct your logical qubit. And eventually this logical qubit will live forever. So that's the point where all these noise mechanisms will not matter that much. If you can correct for that, that's it. Then the whole thing will explode. And we will have quantum computers. So, but we're not yet there. We're getting along. Okay, so I spent quite a lot of time on this part because now I would describe resonators. Actually, you've already seen this picture today. So I'm just going to skip a few slides. And circuit QED, Leandro basically said everything. So I'm just going to describe the parts that I like most about this, that I wanted to highlight. This was an experiment from the Santa Barbara group from 10 years ago already, where they used this model of a qubit coupled to a resonator, where we identify again this two-level system term, the harmonic oscillator, and then the interaction. So you see the interaction is bipolar, and these operators basically preserve a number of excitations, which means that this operator destroys an excitation in the qubit and creates one in the resonator. And this operator does the opposite. So this is kind of like a swap interaction. So based on this kind of interaction, what the group of John Martinez, what they did was connecting a qubit. This is one of the old phase qubits. So this whole thing is the qubit. This qubit was capacitively connected here with this meandering line, which is a resonator. And the idea is the following. So they started with this resonator in the ground state, no photons, and then the qubit also in the ground state, but with a different energy. And then they excited the qubit and brought it into resonance with the resonator quickly, such that this interaction, this swap interaction kicks in, and then the system starts to swap back and forth an oscillation. And this is the bottom trace. This is the bottom one. So you see this oscillation goes from the qubit to the resonator and back, and then decays, because mostly the qubit was quite bad, the phase qubits. But they did something even more neat. They did this process of having this resonant interaction, loaded a photon in the resonator, and then went and excited the qubit again, and brought it again to the resonance of the resonator, and then they had like, the oscillation was between having two photons, and then the qubit excited. So this is basically changing the resonator from Fock state number 1 to Fock state number 2. And every Fock state number because the electric field of a single photon is increased by a square root of n. So that means the coupling grows with the number of photons. And this oscillation is directly the coupling strength. So as they were loading more and more photons, you see these oscillations are getting faster and faster. And in fact, they could take Fourier transforms, and this is basically a square root of the number of photons. So this was really beautiful work. This was the physics of the resonant regime. And then in the dispersive limit, Leandro already told you all the secrets. Essentially, the Stark effect, the Qubit frequency, so the resonator frequency, dependent on the Qubit state. That is the tool that everyone is using today, not only with qubits but with other systems, to read them out in a very, very clean way. So I'm just going to scroll through these. This is a demonstration of the quality of the readout that people have these days with superconducting devices. This is again from the Santa Barbara group. This is one of these pictures. Again, these cross qubit, they call them X-mons, but they're transmon qubits. And this resonator is the readout resonator of the qubit. So this here is the end of the resonator, so it's an open circuit. It's not shorted to ground. So it's a capacitive coupling between the qubit and the resonator. And up here they have essentially a through line that they use to probe this resonator state. And then in the IQ plane, like similar to the data that Leandro was showing, they can distinguish very well between these two distributions of states. And here I don't put the numbers, but this is better than 99%. So you can distinguish these two distributions with an error which is well below 1%. There is also, this is already like a clean measurement, but if you don't do anything, there's also the second state of the qubit, because these transmon qubits are quite, they're close to a harmonic system, as I explained yesterday, so you can actually get easily into the second level, and then you see it here on the IQ plane as a different blob. But there's tricks. You can play tricks to suppress that. Yes?
So is it a projective readout? So when I can read out the state of my qubit with this, then I can project it down?
Yeah, it's a projective measurement. Yeah, and in fact, people have done measurements where they, let's say, they perform a measurement on the cavity frequency, which projects the qubit state, and then they are fast enough, the electronics of their system is fast enough to, again, change the qubit state and then do another measurement. So do kind of like a feedback kind of mechanism. And in this way, they were able to stabilize. This was the group of Irfan Siddiqui in Berkeley. They were able to stabilize single qubit performing Rabi oscillations forever. So because they were able to correct, their readout method is fast enough, the electronics are fast, and then they could do this correction because the readout is projective and it's not destructive. Okay. So this is about the time it takes to perform a measurement. You see that the error rate stays around the 1% level, and sorry, this is the error. So it stays around the 1% level here, where the readout time is about 120, 130 nanoseconds. In these measurements, so what they show is that they send this readout pulse. This readout pulse enters their feed line into the chip, which talks to many resonators, each resonator coupled to a qubit, and then it goes to an amplifier. Actually, this amplifier for this measurement was already used. It's a special amplifier. I'm going to talk about that towards the end. But these are quantum limited amplifiers, which are consist of superconducting elements as well. But this, essentially with these amplifiers, they're able to get a very good signal to noise, which helps getting your signal very fast. Okay, so now we have a good amount of time to talk about qubit couplings and then to qubit gates, which was a question I had yesterday. So now we talk a lot about single qubit. Now let's start putting them together. This was the device that was used in Santa Barbara work in 2014, where they had 5 qubits lined up next to each other. At the time, this was the largest quantum processor ever used with superconducting devices. So these crosses, these qubits, they're close to each other. This is a zoom in of these arms. So these arms, they basically have a capacitive coupling with each other. In this case, it's about 30 megahertz. It can be increased by putting them closer. So in this case, both qubits share a capacitance.